Okay, so we have this, right? So we did something sort of trivial. We divided our force into two parts. We looked at the virtual work done by this force. So the total virtual work has to be zero because we are in equilibrium. And then the parts, since we set one part to zero, the other part also has to be zero. Right, so you write this down, and then you notice that there's some long derivation in the book. I think we don't need that long derivation. What you can do is that you can say that your force is in fact dqi by dt for qi dot. And so because we're in equilibrium, the force is zero. Well, this is also zero. All right, so you put this in here. This is also zero. Y dot delta Ri is also zero. Okay? But and because it's zero, I can just subtract it off from this, right? So this is a dot product. I can subtract this off and then take into common parentheses. Putting these two together, we're going to have our applied force minus the time derivative of our momenta, dot producted into our virtual displacement is going to be zero. Okay? And this is what the book calls D'Alembert's principle. Okay? One reason why this is confusing is because you're not doing anything. Okay? The other reason is that there are different names for this. That different things are called D'Alembert's principle, but this is what the book is calling D'Alembert's principle. We got that along with that. So we have this, and because of this, we are at this point drop the superscript A. We got rid of the constraint forces, so we don't need to refer to applied force versus constraint force. This is just going to be our force, and we drop the superscript, but we don't drop the vector sign, obviously. Okay. Now, here is why not having independent coordinates is a problem. Now, if these were independent, what could you say for this problem? So we have some, vector. So this is in fact a lot of equations, right? So this is looking at this is a sum with a very large number. So this is going from I from 1 to n. But in fact, each term over here is three sums, or a sum with three terms. And then there are actually three n terms in our total sum. Now, and we are saying that this is zero. Now, if these coordinates and hence these virtual displacements were independent, what conclusion could you draw from this? This is a trick that you must have seen before, though of course you might not be recalling it. But it's a very, very powerful thing we are going to use again and again. What can you say? You have some complicated expression like this, and you're multiplying it by a number of variables, A, B, C, D, and these variables have some various coefficients, and this all adds up to zero. And this A, B, C, D are all independent. Then what can you say? So all those coefficients must be zero. This is the only way. If they are independent, the only way I can get this sum to be zero is if all those coefficients are zero. Because otherwise, I could change one of them independently of the others and make it deviate. And if these were just arbitrary numbers that I can pick up independently, and if its coefficient, the corresponding coefficient to that one, was non-zero, I could just change it slightly, maybe increase it, and the sum will no longer be zero. Okay? The only way for independent numbers, right, so let's perhaps write it this way. This is not necessarily easy to grasp. So I'm going to have let's just do this. Let's have something like this: capital A times A, capital B times B, capital C times. So for any value of ABC, this is zero. Okay? And A, B, C are independent. the only way I can do this is if this capital A, capital B, and capital C has to be 0. Now, this argument breaks down if these are not independent. Why? Because what did I say? I said, okay, this has to be 0, because otherwise, if, for example, A is not 0, then I can take my small a, lowercase a, and increase it slightly, and this sum is going to change. It's no longer going to be 0. But if they're not independent, you can't do that. If they're not independent, as you're changing A, your B and C are going to change as well. And they could conspire to make the sum 0 again. You can't make a mathematical argument. But if they are independent, then you can. Then you can say that, oh, this has to be 0. And that would be very nice. Then we would have these very nice differential equations that we can solve and get the solution to our problem. But at this point, we can't, because these are not independent because of the constraints. So what we want to do is to express everything in terms of our generalized coordinates that are, in fact, independent of each other. Right, so we take these transformation equations and we kind of manipulate them, and we write everything in terms of, so we try to get an expression that's similar to this, but in terms of generalized coordinates over here. So we're going to be multiplying certain things by generalized coordinates. And then because they are independent, we're going to conclude the coefficients of those are in fact all 0. And that's going to give me a nice set of equations. In fact, it's going to give me one equation for each of the generalized coordinates, and that solves my problem. So I'm going to get 3n minus k further equations, and that's going to be sufficient. Because I have k equations coming from the constraints, and 3n minus k come from here. So I'm going to be able to solve for all my dynamics, basically. Okay? So this is the plan. Now, to proceed with this plan, we're going to use chain rule. Right? So again, we'll keep this in mind, and also this one in mind, but I'm going to erase them. We are going to just manipulate things using chain rule. And this is going to look somewhat similar to what I did for our first meeting, which I called complete garbage, but now they are going to be actually careful. Again, there's going to be some ambiguity for the left-hand side and right-hand side of the equations, and if that bothers you, that's fine. There is some ambiguity, there is some difficulty, but that's why I'm here. Right? So if you have some difficulties, then we are going to try to tackle them together. Okay, so let's write down our transformation equations. We have a number of these, n of them. So these ones are, I'm going to use, I'm not going to use 3n minus k anymore, and just use small n for this. And remember, this potentially also includes time. Now, we can write down, so for ri dot, we are going to use the familiar notation v sub I, and now I want to write this total derivative with respect to time in terms of some partial derivatives. And so this is going to have the partial derivative of this coordinate with respect to time. Okay. And then we are going to apply the chain rule. Okay. We're going to have the partial derivative of our coordinates. I can always do this. It's a function of all of these with respect to qj, and then the total derivative of that qj with respect to time. Okay. This is the chain rule. This is I'm not going to prove this or try to prove this. This is how, if you have a function of so and so variables, this is how you get this. How you get the total derivative. Okay. So as you see, this can't explicitly depend. If there is no time, then this term just drops out. You just end up with the sum. But we are allowing for the presence of time or dependence on time, and so we keep this partial derivative as well. And likewise, we can also write an expression for our virtual displacement Okay. Again, this is going to be in terms of all those. Yeah, I made a mistake here. Again, this is just a form of chain rule, but now this relates our virtual displacements in our original Cartesian coordinates to our generalized coordinates. And as I said, these generalized coordinates could be anything. Now we go ahead and write the usual force. So I remember this is now with dropped superscript a minus qi dot a. Now, if you are having difficulty seeing my dots, then this is going to be a bit messy. There is a dot over there, so this is the time derivative of the. Sorry, this is p. Now, the time derivative of the momentum, and there's a dot product. There's a dot for a dot product over here. So I just took this and divided it into two parts, and I'm going to manipulate the two parts separately. So let's just call this one perhaps star. Okay. I'm not sure this is going to fit. Let's see. So the star is going to be some sum of I dot. Now instead of this displacement, I'm going to take this expression over here. So some sum over j, the partial of our I with respect to generalized coordinate qj, and then small change in qj. And by definition, I'm going to call this some sum over qj times delta qj. And here I'm defining qj as some sum over I dot del I dot qj. Okay. So this is the definition. So this is a double sum. Obviously, I can move this out without any trouble, and then I can move the other one in and isolate it. And then I end up this expression. Right? So the further steps are in the book, so you can check this for yourselves. I just want to discuss the equations. That's why I'm writing them down. There's no reason, in fact, that these were in front of us. Try this again. So the way you do this is you take this out, you take this in, well, sort of, not completely in. You can also, so this is just a scalar, so you can move it around without a problem. And you define this sum over I over the particles as this capital Qj, and then you end up with a little sum over your generalized coordinates. This one is the generalized force. Now, just like our generalized coordinates do not have to be coordinates, generalized force do not have dimensions of newtons or anything like that. It can be anything. What is required, however, is that this product has to have dimensions of work. Okay? So this has to have dimensions of Newton meter. This doesn't have to be newtons, this doesn't have to be meters, but their product has to be work. Okay? And if you look at the equations, you can convince yourselves that this is guaranteed from the way we define things. Okay? The units are just going to cancel. No matter what unit you choose for this, this is going to have the same dimensions as force times the Cartesian coordinates. Yeah, that's a problem.
John?
But yeah.
The way we defined a generalized force is Fi times dr divided by dq. So isn't it in the dimensions of force? But
No,
Again,
because it's not
you
necessarily
mentioned QI doesn't have to be in the dimension
So
of.
these could have different dimensions. Right?
Okay.
So,
Okay. So the difference comes from QI as well. Okay.
of course, if for some reason, like the simple example I gave, this had the dimensions of length, then yeah, this is going to have the same dimensions. But that's in general not true. Okay, now for the second part, let's call this perhaps double star. And the double star is going to be sum of mi or I double dots dotted into delta Ri. Now I can do this. I can do this because these are, remember, implicitly Cartesian coordinates. Right? So my pi is nothing but mi pi. Okay? And that this is dot, and this is dot, and this becomes mi double dot. So because I'm dealing with my original coordinates here, this manipulation is okay. For the original coordinates, the momentum is always just your mass times your velocity. Now, if you're moving to generalized coordinates, this no longer holds. Okay? There's not going to be an associated mass, in fact. Right? You're going to have a smaller number of, a different number of generalized coordinates than your number of particles. So how are you going to distribute your masses, the mass of particles in these? There are ways, but in general, this is not going to hold. But for the original coordinates, it does. So I can write it this way. And this, again, by using the chain rule, for this one, is going to become a double sum. Okay. Mi or I double dot del Ri by del Qj delta Qj. Okay. So this part, this part became this, and that part became this. Now I've for both of them, I have this variation on my generalized coordinates on the right-hand side, and I have some complicated expressions. I will need to erase this, but I will refer to this later. Let's call this 3 star. But I'm gonna erase some stuff. Now, just keep this in mind, the chain rule for these two things. Hopefully, when you manipulate this a couple of times, it's going to become natural. Now, I want to get something somewhat similar to this. And this involves a second derivative. So I'm going to take the derivative, the time derivative, of something that's similar, but not exactly like that. Right? So I'm going to look at this. So this is just the first derivative, dot producted into I by Qj. Yeah. This one. Now, if I take the time derivative of this expression, I'm going to get something similar to this dot product, okay? Plus another term. So I'm going to get my mi Ri double dot dotted into Ri by del Qj plus some additional term that I'm going to handle. This is going to be mi Ri dot dotted into d by dt del Ri by del J. Now, this is just VI. And I'll try to write everything in terms of velocities because that's what I'm going to end up with. Okay, this is just VI. This one This is also VI. This one is del VI by del QJ dot. Okay. So this expression is the partial derivative of Ri with respect to Qj. I'm claiming that this is the same thing as the partial derivative of the velocity with respect to time derivative of the generalized coordinate J. How would you go about showing this? How would you do that? Did you do something like this before? In MT perhaps? I don't know. I don't know if you went that far. Or for the first, for the undergraduate classical mechanics. Or differential equations.
Can we use chain rule?
You use chain rule, yes. That's the thing. You always use the chain rule. Right? So you write this, and then you write things in terms of well, it's easier to start with this and get this one, yeah, because of the yeah, you use chain rule. Maybe I'll make this a homework. But I'll check if it's in the book. If it's not in the book, I'll make it a homework. So this is a good exercise that you learn how to manipulate these things. And this one also becomes del VI by del QJ. Okay. All right. Now we want to take this expression. So we had this expression in our, what I marked as 3 stars over there. So I'll take this and write it as the left-hand side minus this additional term over here, but using V's. Yeah, so I Ri double dot del Ri by del Qj is going to be d by dt of n vi dotted into del vi by del Qj minus this thing over here m vi dotted into d by dt. Oh, I prefer to cut that. Sorry. Partial vi by Qj. Okay. And then you take this and you put it into that 3-star argument and expression. You get, and this. I need a bigger board. Can you follow this? This is a. I mean, if it's the first time you're saying, I imagine you can't. But I don't know what to do. I have to erase it. I just need the room. Can you actually take these down, or do you have difficulty following? Do you need me to go back? Because once I erase it, if you ask me to go back, it's impossible. That's why I'm asking and try to slow down. Okay. I also turn on the chat just in case somebody writes something there because I can't hear them or something. Right. But now we take this and put it into expression, that 3-star. I think it was 3-star.
There is a dot in the derivative part, right? D by dt parentheses. It is dv.
Yes, this is a dot product. So this is the MVI dotted into partial of VI to QJ.
The QJ dot, is it?
Oh, yes. Yes.
All right.
Yeah, thank you. Otherwise, this will be trivial. Yeah. Now, so that thing becomes J. So what is this? MVI by divided dt.
It is the left-hand side times virtual displacement.
Oh.
So it is equivalent to the right side as well.
Yeah, no. So no, I'm looking at this expression. This is what you would get when you take the derivative of VI squared with respect to QJ dot. So the dot. Yeah. Is this correct? I think so.
Hocam, Dennis is asking in chat if you can make the dots a little bit visible.
Okay. I'll try. So these are the non-trivial ones, I think. So this is correct, right? Yeah. So then we add the m, and we take you at a half. We end up.
That gives us the kinetic energy of.
Yeah. That's what I'm trying to get. So it's going to be del by del G dot a half mi vi squared. So I'm just using this to manipulate this one. So over here. And then the second term, this one also can be manipulated the same way, but instead of partial derivative to QJ dot, it's going to be partial derivative with respect to QJ. This is going to be minus del by del QJ a half m pi square. Yeah, and all of this is multiplied by del QJ. And as your friend correctly stated, this is kinetic energy. This is kinetic energy. And so we can write, I'm going to need to erase this. So if you also put back the expression with the generalized force, we're going to end up with the sum over this Qj minus d by dt of del T by del Qj dot minus the partial of kinetic energy by Qj times delta Qj is 0. Our original expression turned into this. And this is great because these are independent of each other by definition. We took out the constraints, they are not independent coordinates. And because these are independent coordinates, all of these, term by term, has to be 0. Now, there is one final manipulation that we are going to do. And we're going to just take this generalized force and write it in terms of some partial derivatives of the potential. Okay? Now you know this already for our original force. So RFI are minus the gradient of your some potential. Okay? And again, you're going to apply the chain rule to this. This is done in the book. This one I'm sure is done in the book, so you can check this out. But what you end up is that you're going to have Qj is equal to minus, book is using V, I think. V, partial of V with respect to Qj. Yeah. You could almost guess this, right? Because otherwise there would be no point in calling these coordinates. But this generalized force, I'm calling this generalized force. This generalized force is just the partial derivatives of your potential with a negative sign, just a convention. Okay? And because of this, you take this and put this in, and you can then connect these, or put these two terms together. And oh, I made a sign mistake. I have a sign mistake somewhere. This is plus. Yeah. Plus. You can take this, put these together, and you're going to end up with the partial derivative of T minus V with respect to Qj. Okay. Now, our potential, so this is, there's a dot here. V is depends on our Qi. Okay. It does not depend on, explicitly at least, on the derivatives of this generalized coordinates. Because of that, the partial derivative of V with respect to Qj dot is going to be 0, which means I can arbitrarily add or subtract V into this. Its partial derivative is always going to be 0. Okay. So I wrote this Q in terms of V and combined these two terms. So that gave me something like T minus V. And I'll just, by hand, subtract off V from here. It's not going to change anything because the partial derivative of V with respect to derivative of the generalized coordinate is 0. And so I end up the equation that d by dt of the partial of T minus V by Qj dot minus, this was minus, so this is now going to become a partial of T minus V with respect to Qj is going to be 0. Okay. And because we have such a nice little expression there, we're going to call this T minus V our Lagrangian. By definition.
Hocam
And,
QJ or 0?
sorry?
0 or QJ?
0. Qj is absorbed here. Okay. Without this, that will be Qj. With this,
Okay.
right? So I took Qj, turned it into this, and then subtracted off. I didn't do all the manipulation because it's just becoming useless. I'm just erasing things all the time. I want to keep important things on the board, but perhaps I was too hasty. So there was an expression over here that involved the partial derivative with respect to partial derivative of the kinetic energy with respect to Qj, plus this capital Qj. Then I recognized that this capital Qj is in fact the partial derivative of the potential with respect to Qj. So I put those terms two partial derivatives together. And this became kinetic energy minus the potential energy. Then I arbitrarily, so this there was this, the total time derivative of the partial derivative of kinetic energy with respect to the time derivative of the generalized coordinates. From that, I just by hand subtracted the potential energy. I can do this because this the potential energies partial derivative with respect to derivatives of the generalized coordinates is 0. My potential does not explicitly depend on the derivatives of the coordinates by assumption. And for that case, I get this nice simple equation, just some partial derivatives of this T minus V, the kinetic minus potential energy, and I'm just going to call this the Lagrangian. And you probably caught this, but we use Newton's equation of motion F equals ma for this derivation, and it turns out that this formulation is equivalent to that formulation. One nice thing is that this is in terms of generalized coordinates. This will be somewhat hard to write in terms of generalized coordinates, though this shows you how to do it. Okay? Given the potential, you express it in terms of your generalized coordinates, and then taking partial derivatives is going to give you some generalized forces. But this is more suitable for certain problems. So it's going to be some time before we actually solve a problem that can't be solved by other means. Okay. Now, this is, I think, again, a good point to take a break, another 10-minute break. So we are up to this point, we kind of neglected certain kinds of forces, like the friction, dissipative forces, things like that. Now, there is a way to include them. And that is, in fact, what your friend suggested, that adding them by hand. So any force that we can express as a potential can be absorbed into our Lagrangian formulation through this. Some forces, like friction, which are not conservative, cannot be expressed through a potential. And those we can't absorb into this term. They're just going to keep over here. And there's a section on the book for this, but I'm going to kind of skip it. And if necessary, we are going to come back to this. This is all I'll say at this point, that you can include forces that are not expressed by potential this way. Just put them on the right-hand side. So this is one form of Lagrange equations. If you want to include dissipative forces, you'll just add something over there. And now we'll take a break.